everybody. So just give it up for Joe. I always love seeing Joe give presentations, not just because he's a Rigetti customer, but he's one of the rare breed in this industry of folks that are not only deeply versed in quantum information science and the systems associated with it, but he's a world-class software developer, computational science. He understands deeply about things like compilers, things that really actually matter as we start to build out systems. Here we go. Cut right to here. So we've been at this for a while. We've got a few firsts in the industry that we're quite proud of. First multi-chip, first high-performance hybrid system, first highest qubit count system always on Amazon. We were a foundational partner at Fermilab's SQMS Center. At 140 people, we're small but a very mighty team. And sort of son of a gun, as of this morning, we're pretty close to a $2 billion market cap, which I'd like to say, thank you, Google. It was a very nice announcement yesterday. So today I'm going to talk about how we're using I'm going to give you a sort of a preview of our roadmap and talk about a few things that are relevant to our long-term future, as well as talk in some detail about what is happening in 2025. Perhaps the most important first that we have in the industry at this point is the first sort of all-quantum, fully dedicated fab, captive fab to the organization. I've talked at length about this before, but it can never be overemphasized in terms of the impact it's had on the company and the ability for us to do what it is that we do. Perhaps one of the most interesting examples recently of the fab delivering innovation quickly and into product is the invention and adoption of our alternating bias assisted annealing process, ABAA. ABAA is a process for precisely tuning our qubit frequencies. This is, it's actually a process for precisely tuning our JJ resistances, but the relationship there is direct. Instead of using lasers, as most processes that tend to go about solving this problem do, we use an alternating voltage applied directly to the JJs, and it enables us to get an order of magnitude increase in performance of targeting our qubits. This has been a tremendous value in terms of as we've moved down the path towards higher fidelities. Of note, and again, underlining the business around fab, we went essentially from idea to experiment to paper to production in less than a year. ABAA is now part of our process of record for all of our production qubits and tunable couplers, and it's been an important part in our overall journey towards increasing our fidelities. With respect to increasing our fidelities, as you might imagine, I really, really love this plot. For the past couple of years, we've been focusing on decreasing our error rates. We've successfully cut our error rates in half for each successive milestone system that we've released. We expect to continue doing so into next year and beyond. With that, though, I'd like to introduce you to Ankaa 3. Ankaa 3 is our newest 84-qubit Ankaa-based system. It's, as promised, delivered at the end of the year with a 1% error rate, 1% median error rate across all 84 qubits. Ankaa 3 is a fairly extensive redesign of hardware, including a very light, very thermally efficient new tower. It also, as I said before, incorporates ABAA as a key process in terms of enabling high fidelities. It also supports essentially a redesign of the layout of the underlying qubits, both qubits and tunable couplers. It's going to be available, as I said, this year. It'll be available on Rigetti's quantum cloud system, as well as available on Amazon and Microsoft's Azure system, and I suspect a few other cloud systems moving forward. You'll also remember a minute ago when I talked about the sort of first multi-chips. We did this back in 2021, I think, was the first sort of 80Q system made out of 40Q. Multi-chip helps us with yields in that it allows us to cherry pick our qubits. It generally gives us flexibility when it comes to scaling strategies. And it leverages a very mature 3D signaling system that we've been developing over the years. And critically, it seems to perform as well as single chip systems. What I mean is qubits that entangle across the die boundaries perform as well as the qubits that entangle intra-die. This has been critical to our long-term thinking, and so for 2025, we're going to begin to make use a little bit more of this. So we intended to introduce 2 new milestone systems in 2025. The point here, the path here is about continuing to decrease our error rates, increasing our qubit count, while increasing the density of dies that we use as we build these larger systems. This system, in Q2, we're going to introduce a 36Q system at a 0.5% error rate, and this system will be built from 4 9Q dies. These are the same 9Q qubits that show up on our traditional 84 qubit systems. It also turns out that these are the same qubits that show up in our 9Q Novera systems. I'll tell you a little bit more about that later. This will be the first time that we've, on production systems, used more than 2 chips, but early indications are actually quite positive. Now, in Q4, we'll be introducing an 84Q system at 99.5% fidelity. It's a 0.5% error rate. And the goal there is overall to continue to half our error rates moving forward and increase the number of qubits in the system. So by the end of next year, we will not only have we will not only have good multi-chip systems out there, but we'll have large qubit count systems out there. With the introduction of Novera last year, at last year's Q2B, in fact, we noticed people got a little bit confused over what our overall product offerings are. So I'm going to go over these with you today. We essentially go to market with 4 things. The first thing we go to market with is quantum computing systems. These are 24 qubits to 84 qubits. These are designed for national labs, regional labs, HPC centers, national quantum computing centers, and they are full systems. That's in contradistinction to the second thing we sell, which is QPUs and then associated foundry services. A QPU in this context is like the Novera system. It is the chip, but it's a little bit more than the chip. It includes the necessary signal process or signal chain componentry, the cold finger that attaches to the bottom of the dilution refrigerator. Really, it's designed as a unit that can plug directly into a dilution refrigerator that's been properly cabled, and then you can hook it up to the control system of your choice. In addition to the Novera QPUs, we also do foundry services where we sell some small capability chips. We also do modifications with select customers on those chips. And I'll talk a little bit more about a very good project that we're working on that we think is going to have a lot of legs. Third thing that we do, quantum computing as a service. So all of our milestone systems are available on our QCAS system, QCS Quantum Cloud Services. In addition, we put our systems up on all of the public clouds and in some cases direct connections to certain enterprises. Finally, and importantly, we do an awful lot of application and research service work. And what that means is we work with government agencies and some industrial partners to further our research agenda and theirs with all of the capabilities that we can bring to bear. Sometimes it's chip work, sometimes it's algorithm work, and sometimes it's just using the latest system as efficiently as we possibly can. I feel compelled to talk a little bit about what it means to field a full computing system. That definition is very weak in the industry, generally speaking, and it's important to understand that it's much more than the chips themselves. And in fact, let's just imagine that you've mastered the several disciplines necessary, manufacturing, engineering, physics, in order to field a high-performance chip, and you've gotten it in a dilution refrigerator, and the thing is up and running. Unless you're a physics grad student, or a postdoc, there's not a lot you can do with that system. Most people immediately add a control system. You need a control system, of course, to actually manipulate the qubits themselves in a controlled fashion. It also serves as the front end to the rest of the world to actually use your quantum computing environment. You can probably, with the software associated with the system itself, do some work with a control system, do some work usefully, but it's not trivial. Really, what you want is some form of language to write your programs in that manipulate the quantum computer. And with the programming languages come compilers and executables and binaries. And of course, you need something to submit the job you created. Maybe you need something to actually manage multiple jobs that you've created. You need something to actually deal with return values, et cetera. There's a whole lot of software. It's effectively an operating system. Oh, and by the way, as anyone who's actually operated a quantum computing system will know, you need to actually calibrate these things before you can use them. And then during use, from time to time, they need to be recalibrated for stability purposes. This also implies a tremendous amount of additional software and automation. Note, it's one thing to try, and we've seen this over and over again as we've launched Novera, it's one thing to try to calibrate to high performance a couple of 3, 5, even 9 qubits. 80 qubits, 100 qubits, it's a whole other story. So you end up needing quite a bit of optimization software as well as automation software to make this work. If you're an HPC center or a National Quantum Computing Center or an industry, you need additional services such as billing, reservations, account management, and all of that. If you're a National Quantum Computing Center, usually have an agenda to support the entire country, and that means you probably need to make these resources available over the cloud to a much broader consortium or group than the folks that are in your National Quantum Computing Center. Also, it may well be that you'll want folks like Rigetti to be able to manage the system remotely for you, which is also a service that we offer. So it's all this stuff that we deliver, as well as the classical compute and the networking equipment necessary to bring it into your system. And this is what we mean when we talk about a large-scale Ankaa-class quantum computing system. When we deliver these things, we deliver, as I said, all of these things as well as a little bit of additional equipment, and we deliver it to performance specs. And we don't stop until the thing is up, running, and performing to spec. Now, one of the things that we don't do is we don't take that system and lock it in a room and put a guard in front of it and say, you can't touch it. There are a variety of levels in which you might want to do replacements and integrate either your equipment, your software development capabilities. Maybe you have a research agenda that requires modifying certain things, and this is not something we prohibit. We will deliver a system to you fully functioning with our own components, including control systems and all the rest, because inevitably what was asked for when it's being delivered is a high-performance thing. But if you've got the desire to bring the system up yourself, to replace the software that we used to do the bring up with your own software, to replace the control system, if that's what you want to do, we're certainly not going to get in your way. Now, the guarantees of performance will be modified as you start to do your own work here, but that's only to be expected. I talked a little bit about Novera and the QPU itself. This has been a really exciting thing for us in the last year. One of the things that we found is that there are a wider variety of use cases for this system than we ever expected. You just saw Joe talking about the things he's doing with a Novera. There's even more than that. They have them at AFRL, they have them at Fermilab as well. There's a few other places that are using them. We've got a robust partner program, which I'll talk about in a moment, that is sort of bringing together a really wide group of people to build an ecosystem around this thing. The other thing that's really important is that if you want one of these things, we can get them to you immediately. And by immediately, I mean if you really want a Novera today, you come to the booth, talk to us, and we'll see if we can put it in the mail, ship it to you, relatively, within the week, essentially. We keep a few of these things on backlog. They're fairly easy to build for us, and they do maintain the same high performance standards of our Ankaa systems as well. Quick shout out, Spectrum Lab at Montana State University has got one in the mail as we speak. I think it's arriving within the next week or so. It was a little bit remarkable after I gave the same talk, or a similar talk last year, and we were introducing the Novera. Within hours, and in fact immediately after my talk, we were surrounded by people that were interested in participating. We had groups of people who were saying, oh, we want to work with you to get our software into people's hands who have Noveras. We'd like to ship with your project. We had people who had control systems that wanted to do bundles. We talked to a broad collection of dilution refrigerator manufacturers that also wanted to do this kind of work, and in some cases, some of them were interested in using it internally. So we built, in the spring, we launched a partner program. We are currently 16 members in that partner program. The two most recent members are Quantum Elements and Cruise. those two folks, along with Trek Quantum Machines and Oxford Instruments, were part of a challenge to demonstrate the value of high-performance machine learning-enhanced control software. This whole thing took place on a Novera at the Israeli Computing Center. I don't have time to talk about the results here, but the work that these folks are doing is remarkable, and Novera is turning out to be a really valuable test bed for a wide variety of use cases. I talked a little bit a minute ago about one tact we take in terms of going to market, and that's working closely with partners. For the most part, what we do whenever we work with a partner is we align our mutual research agendas. It only works if both organizations are looking for an outcome that moves their business forward. I'm going to do a sort of glancing view of a half a dozen programs or so, sort of get you a sense of the kinds of things we do and why we do them. When we signed up to provide a 24-qubit system to the National Quantum Computing Center in the UK, Michael Cuthbert, their director, asked us specifically, he said, look, the ideal case here, the win for this system, is if when I open the doors and bring the minister in, I have an operating high-performance quantum computing system that people can use. Can you do that? Well, as is often the case with these things, right? The building isn't open in time, the room isn't the right size, there's not quite the electrical capabilities. Oh my goodness, the control system isn't going to go in the place that you thought it was going to go. And it's sort of par for the course. But I am very proud to say that the team managed to pull this one off. And when the minister showed up last October, when they opened the doors, we were the only functioning quantum computing system in the building. And I think that remains true to the day. So they got what they needed. And this is the kind of thing that sort of we love to be doing. That same team, or at least an extension of that same team in the UK, has been working on quantum machine learning for finance for a while now. One program done with Idea Labs, this is an Abu Dhabi research organization, is essentially a machine learning classification program augmented by quantum. In this case, it's really just classifying samples from an unknown multivariate distribution. Really what we're talking about is you get a time series, you want to take a few samples, and you want to decide if it's part of a particular distribution that you know or not. What we found when we were doing this work is that there were augmentations to the classical algorithms that started to produce results that were slightly better than the classical ones when run on our QPUs. Note that this gets better as performance gets better. So we're feeling really quite confident about this thing being something important for the organization that we're working with. Another one is a partnership we have with HPCC, NQCC, and the University of Edinburgh. This is a rare event detection algorithm that they're going to talk about tomorrow at a talk. I'm not going to go into any details here. They'll give you what you need to know about that, and all the papers are available and easily findable. Now this is really exciting. We've been working with Riverlane for a long time now in a variety of ways, since their early days and even to some extent our early days. Recently, Riverlane published a paper with a couple of Rigetti co-authors here describing experiments run on our Anka 2 84Q system. This system used a modified control system that had their FPGA with their decoding algorithm in it. They performed an 8Q stability experiment with 25 decoding rounds, up to 25 decoding rounds, and they managed to get decoding times faster than the 1 microsecond limit for superconducting qubits. This directly addresses the backlog problem and shows that you can actually get low latency feedback for QEC results in the appropriate times. We've been working with DARPA for a long time. We were part of the early HONEST program. We were part of the original quantum benchmarking program. We recently did a DARPA impact thing. The thing that I want to talk about here is that the hallmark of our participation in all of these programs is that we use a tremendous amount of QPU time in doing any of this work. This is not a bunch of simulation. This is all actual QPU time. And in fact, it was noted in the ONYX program that the amount of actual QPU runs done by the Rigetti submission was something like an order of magnitude more than anybody else. So the thing that we like when we like to engage on these programs is to be able to actually bring the feedback back from what we're working on to the teams that are working on the hardware, and in some cases the software, if you think about the gate architectures as being software. A real deep focus on hardware integration is the kind of thing that sort of tickles our fancy when it comes to programs that we want to work on. Here's another project that I'm especially excited about, and this one just underlines once again the value of having a captive quantum fab. What we're doing with QFox is we're integrating their transduction capability. So this is the idea here is we want to be able to do transduction from optical through a superconducting connection, and this requires modification of our qubits in order to support their technology. At the end, we hope, and I don't think this is going to be too distant, but my hope is that we're not too far away from being able to set up a lab with a number of Noveras connected up for networking experiments and quantum computing experiments of multiple systems operating in tandem. And then finally, I'd like to talk briefly about a long partnership that we've had with Q-Control. We've been working with them for many, many years. They were with us early. We did some characterization work and simulation work with them. It's well known that Q-Control is doing valuable work in bringing real-time applications closer to reality with their infrastructure solutions, including the AI-driven gate optimization, and they've got circuit-level error suppression that's being integrated. Their product, Fire Opal Native, is something that we're working on integrating into our system as we speak. There's likely to be an early access, and if anybody is interested in participating in that early access, please come see us in the booth, and we'd like to give you a quick look at it. All right, finally, everything that we do is sort of directed and is supported at heading towards fault tolerance. All our internal roadmaps are driving us there. The work towards better fidelity, scaling, integration with classical machines, the stuff that we were doing with Riverlane, all of this reads on that for sure. But as we approach systems with a few hundred, maybe a couple of thousand qubits at error rates of 0.5%, 0.25%, a tenth of a percent, we have in our hands a computational resource that the world hasn't really seen yet. Through the flywheel of design, implement, experiment, repeat, we're going to continue to learn what we can do with that computational resources, and we're going to build systems around it. We'll do everything we can to use that flywheel to put those systems to practice on the road to logical qubits. Thank you for taking the time to listen. Sorry I went over a little bit, but it was really a pleasure to talk to you all.